Earlier we learned how to solve probability problems involving rolling two dice. An example might be something like this. If E is the event that the sum is 5 when two fair dice are rolled, what is the probability of E? And the way we solved that was by noticing that we have a 36 element sample space of equally likely events, equally likely outcomes. There are 6 by 6 possibilities. We've done this many times for a total of 36 possibilities total, and they're all equally likely. Then we apply the basic probability principle. The basic probability principle says that the probability of an event E is the number of ways E can occur over the number of elements in the sample space. Now to find the numerator, the number of ways that E can occur, we simply look at the equally likely sample space, those 36 possibilities, and as we look through all 36 possibilities, there are exactly 4 where the sum is 5. 4, 1, 3, 2, 2, 3, and 1, 4. So the numerator of the basic probability principle formula is 4. And as we've already noted, the number of elements in the sample space is 36. So by the basic probability principle, the probability of the event E, which is that the sum is 5, is 4 over 36. And of course, you shouldn't forget to reduce that. That reduces to 1/9. The point here is this is something that we've been doing for quite some time, and you're probably good at doing this by now. But I want to make a slight change and add a twist to this. Now suppose that I give you some extra information before I ask you to calculate that probability. In other words, I'm going to give you some information that you didn't have earlier. And here it is. What if I tell you that I've already peaked and I know that the sum is odd? Does that matter? Does that have any effect on what you now think the probability is of the sum being 5? I would hope you agree that the answer to that is obviously yes, it should matter. If you look at the sample space, if I know that the sum is odd, all the even sums can be eliminated as possibilities. If I've already told you that the sum is odd, you're not going to have a 2, 2 or a 3, 3 or a 1, 5 because those sum to even numbers. So the only thing you're left with are the 18 odd sums, 2, 1, 4, 1, 6, 1, 1, 2, 3, 2, 5, 2, and so on. So that modifies the basic probability principle result that we got earlier. So this is going to change, or at least I believe it will. Let's have a look. To sort of acknowledge the fact that I expect these probabilities to change, I'm going to actually change the way I worded this. I'm going to say that now instead of just calculating the probability of E that the sum is 5, I'm going to modify that slightly and say that I'm calculating the probability of E given that the sum is odd. And then my answer will still be by the basic probability principle, but it's going to be a possibility of those numerator and denominator values changing because the sample space changed. So my acknowledgement here by rewriting that is that it's very likely that these numbers will change. Well, look, what did they change to? Let's have a look. It's actually pretty easy to see here that the numerator did in fact not change. It might have, but it didn't, because none of the odd sums none of the sums of 5 got marked out. So that 1, 2, 3, 4, 4, 1, 3, 2, 2, 3, and 1, 4 did not change. It might have, but they happened not to get marked out or knocked out of the sample space. But the denominator did. The denominator changed to 18 because half of these sums are even and they're not under consideration once I know the sum is odd. So that means that the numerator stayed 4, the denominator changed from 36 to 18, that'll still reduce to 2/9, but notice the probability changed from 1/9 to 2/9. It's twice as likely that you're going to get a sum of 5 if you know the sum is odd, because the numerator didn't change at all. The denominator got cut in half from 36 to 18. So it becomes twice as likely you're going to get that sum of 5. Of course, the point of my doing this particular example is to introduce a more general idea, and that is when you have a probability which includes an extra condition, the condition I used here was the sum being odd, that probability is called a conditional probability. That's a conditional probability. And we have a special notation for it. Remember that originally I introduced this modified way of writing a probability where I had the condition. I'm going to formalize that now and change it. Now I'm going to say that this is the new notation for that. This is the way I'll write it. The probability of E, the vertical line is read, if you're reading out loud, is read given that. So that's the probability of E given that, and then the condition is read next. So that's the probability of E given that F occurred. The probability of E given F, if you want to say it in sort of as concise way as you can. The probability of E given F. The vertical line is read as the phrase given that. That's called a conditional probability. I might also add that even though I was naming those events with E and F, in reality, if you're dealing with a sentence with all these words in it and no letters, you don't have to introduce the letters. You could just write this as the probability that the sum is 5 given that the sum is odd. You don't have to put E and F in there. Just a convenience. Sort of collecting things together and putting them in a more formal format now. Here's the definition. When we compute the probability of event E, assuming that event F has already occurred, we call this the conditional probability of E given F. We denote it with that notation with the vertical line, as I showed you earlier, and it's read the probability of E given F. Let's change perspective a little bit and look at these in terms of Venn diagrams. The first Venn diagram I have up there shows the intersection of events E and F. That's the yellow shaded area. And the number of elements in E intersect F will be the numerator, as you saw in our previous example, of a probability calculation with conditional probability, just like you saw earlier. The second Venn diagram shows just the probability of event E. Everything in the circle E is in green, and that would be the number of elements in the set E. And the last Venn diagram shows in blue everything in circle F, so that's the number of elements in F. And given all that, you can sort of see the basic probability principle, and let's look at them one at a time. The probability of E given F is the number of elements in E intersect F. That would be this right in here. Divided by the number of elements in F itself. In other words, the whole thing. So the conditional probability is the overlapping part over the whole. And if you want to know, that's the probability of E given F. If you want to know the probability of F given E, that means E has already occurred. That would be the number of elements in E intersect F. Again, I'm looking at this one. That would be inside of here over the number of elements in E, which would be everything in the circle. So what I'm trying to show you is when you're doing these conditional probabilities, if you think about it in terms of Venn diagrams, you're taking part to whole as with all probabilities, but you're taking the intersection of the two events as the numerator, and then you're dividing by, well, it depends on which one you're looking for. If you're looking for the probability of E given F, then you're dividing by the number of elements in F. And if you're looking for the probability of F given E, you're dividing by the number of elements in E. So the denominator is always determined by the condition, the F or the E. The numerator is always the number of elements in the overlap. So I think maybe Venn diagrams can help you see a little bit better where these formulas are coming from and how they work. I do want to add something. I'm not so concerned that you follow the derivation of it, but I do want to emphasize result. If you take that result we just displayed, and if you divide both the numerator and denominator of those two fractions by the number of elements in the sample space, you will get an equivalent result, and it's sometimes better to look at things that way. And what I'm saying here is, if you take, looking at this one, if you take the number of elements in E intersect F and divide it by the number of elements in the sample space. Of course, if you do it to the numerator, you've got to do it to the denominator too, so you get the number of elements in F divided by the number of elements in the sample space. Well, this numerator, when you divide part over whole, you get a probability, so that turns into the probability of E intersect F. And again, when you divide a number representing a part over the whole, that again turns into a probability. That's the probability of F. And you can do the same thing over here. If you divide the number of elements in E intersect F by the number of elements in the sample space, that turns into a probability. And if you divide the number of elements in the set E and divide it by the number of elements in the sample space, that turns into a probability. So again, I'm not really concerned so much that you follow along too much with the algebra here. So I'll get rid of all of this. But what I do want you to pay attention to is the result. So what I've just shown you is that the probability of E given F can also be written as a probability over another probability rather than just counting numbers over numbers. And the probability of F given E obviously can as well. So there are two ways of looking at it. You can look at the conditional probability in terms of the counting, which is what we did earlier, or you can look at it in terms of probability over probability. Same thing in both cases. They're just two different ways of looking at it. They're equivalent. And just to clear up the clutter and putting things together in one place where you can see them better, I'm listing the definition of conditional probability, and I'm also listing those formulas that we've derived. Put them all in one place. I do think that you will find when you're dealing with equally likely sample spaces, it's probably going to be easier to use that first way of computing conditional probabilities with the number in the intersection over the number in whichever event is appropriate. I think you'll probably find it easier to do it that way. But there will be uses for the other formula, especially in another guise. We'll talk about that shortly. Let's do another example. If two cards are drawn without replacement from an ordinary deck of cards, what is the probability that the second card is a heart, given that the first card was a heart? Just a word of advice. When you read through a problem like this, it's important to highlight the significant information and to sort of summarize it. So that's sort of what I've done here. I've noted that you're drawing without replacement. That means when you draw a card out, you don't put it back in before you draw the next one. And the condition is that the first card was a heart. That's what we know has already happened. So given that, think about a deck of cards. There are 13 hearts in a deck of cards, and there are 52 cards in the whole deck. And I've sort of summarized that down here. Before we drew anything out, there were 13 hearts and 52 cards. But if I know that the first card was a heart, after that first draw, the number of hearts went down to 12 because I drew one out, and the number of cards went down to 51. So after that first draw, but before the second draw, I no longer have a deck of 52 cards with 13 hearts. I have a deck of 51 cards with 12 hearts. So now that I know that, it should be a fairly easy matter to calculate that probability using the basic probability principle. The probability, and what am I looking for? I'm looking for the probability that the second card is a heart, so I'll sort of abbreviate that. Second is heart, given that the first was a heart. Was a heart. And of course, that's going to be the basic probability principle. After I've drawn the first heart, I'm now looking at this line. I've already drawn a heart, so I'm down here. I'm down here. So the probability that the second one is a heart, well, there are 12 hearts. But remember, there are only 51 cards left in the deck at this point. There's 12 over 51. Now before you relax, always check to see if something reduces. Now, I think a lot of people don't realize that 51 is not prime. Actually, 51 is not prime. It will divide by 3. 12 divides by 3 and gives 4, and 51 divides by 3 and gives 17. Now that's a common mistake to leave that unreduced thinking that 51 is a prime. But after you've seen it a couple of times, then you know. It's a very simple, straightforward conditional probability problem. Okay, let's look at another example. A container has 35 green marbles, 20 blue marbles, and 4 red marbles. 2 marbles are randomly selected without replacement if the event E is that a green token is selected first and the event F is that the second token is not green, then compute the probability of F given E. Now let's go through and note some of the significant things. We know we're going to need them. First of all, if there are 35 green marbles, 20 blue marbles, and 4 red marbles, that means we have a total of 35 plus 20 plus 4, which is 35, 45, 55 would be 59 in all. That's going to be important. We're selecting without replacement. That means after the first one comes out, we don't put it back in before we select the second one. Event E is that a green token is selected first. And event F is that the second token is not green. So what we're concerned with is green versus not green. So really, we don't care whether they're blue or red. So another thing you might note along the way is that the blue and the reds kind of get lumped together. There are 24 non-green marbles. So that's probably going to be important. We're just looking at green versus non-green. Whether they're red or blue is irrelevant. This is the kind of thing you need to do when you're looking at a problem like this. Look through here and find out what's important or what you think is going to be important. Now we should be able to do the conditional probability. However, I will make a little chart as before. Let's think about before you draw the first marble out. What is the situation? Before the first draw. Well, I've sort of listed it up here, but let's formalize it. Before their first draw, there are 35 green. And again, I don't care whether they're blue or red, it's just whether they're green or not. And there are 24 non-green for a total of 59. I had already done all those calculations, but I just want to organize it. Now what happens after the first draw? After the first draw, well, let's see. What did it say? The event F is that the second token is not green. So if the second token is not green, I want to calculate the probability F given E. So that's the probability that the second token is not green. That's the F. Given that the green token is selected first. So what I know now is what's already happened is the green, the E, which is the green one. So if I've already drawn a green, then I only have 34 greens left. I didn't draw a non-green, so none of the non-greens did change. So I still have 20 blue and 4 red marbles. I chose a green, but that does reduce the grand total down to 58. Now it's just a matter of calculating the probability that they're asking for. So we want to know the probability of F given E. Now, I like to see this in words. I'm going to translate that. The probability of F is that the second is not green, given, and E is that the first one is green. I like to see this in words. So that's what they're asking us to calculate. So that's going to be the probability after this first draw has already happened. So after this first draw has already happened, we're looking for the probability that it's not green. So we've got to have the number of not greens, or non-greens, divided by the total, or the number of elements in a sample space, which is now gone down to 58. Remember, we're looking at what happened after the first draw. So there are only 58 things total, but now we're looking for the number of non-greens. Well, there are 24 non-greens, so that's 24 over 58. And again, you need to make sure that reduces or not. And I know it's even, so it certainly goes by 2. I'll try that. So that's 12 over 29. 29 is prime and 12 doesn't go into 29, so that means that's as far as you can go. So the probability of F given E, which is a probability that the second is not green given that the first one is green, is 12/29. Again, very straightforward. You have to be careful. The more you organize, take your time, highlight the important information, the better off you're going to be when you're solving these problems. Let's look at another example. It's a little different, but in the long run it's the same principle. It says the graph has stats about distracted drivers below the age of 40 who are involved in fatal crashes. If one driver is selected from the 2,767 tallied, and if a driver in this group is under 20, what is the probability of the accident being related to cell phone use? And again, we want to go through this and extract the important information. We have a total of 2767. That may come into play. We know that the driver in this group is under 20, and we want to know the probability of the accident being related to the cell phone use. So I hope what you've noticed by reading through that is they've given us a condition. If a driver in this group is under 20, that's the condition they've given us in that problem. So this is a conditional probability. So we want to know the probability of the accident being related to cell phone use. So the probability that the accident relates to cell phone given this condition. The condition is that the driver is under 20. Under 20 age group. And again, we know we can use the basic probability principle here. So we just need to find the numerator and denominator. Well, the condition is that we're in the under 20 age group. That's here. So our sample space gets reduced. And as you can see now, this 2767 is not even going to matter anymore because our sample space went from 2767 down to whatever the number of drivers are in that group. And we can find that fairly easily. There were 515, and that's the dark is the non-cell phone. And there were 140, and the light is the cell phone. So there was a total, add those together, 5, 5, 6. There are a total of 655 drivers in this group here, and that's the only group we're interested in. So we want to know the probability that the accident relates to the cell phone. That would be the 140, so that goes in the numerator, over the probability of, over the number in the whole group, which is the 655. Now, this particular problem, I believe, wanted the answer written as a probability down to the third decimal place. So let's do that. 140 divided by 655. And if I take that to 3 decimal places, I get 0.214. So the probability is a little more than 21% that the accident related to a cell phone if we know that the driver was in the under 20 age group. Now let's go back to that formula we derived earlier for conditional probabilities, the one that involved using a ratio of probabilities to get the result. Although, as I mentioned at the time, we may seldom actually use that formula for finding conditional probabilities, it does have a guise under which it's very useful. And that's in this form that I've written it in here, which is called the product rule for probabilities. And all I did to get that, not that you have to be able to derive it, but all I did is I took the equation the original equation and multiplied both sides by the probability of E. And when I do that, I get the probability of E intersect F, that's this, is equal to the probability of E, which is this, times the probability of F given E, which is that. So that version, that way of looking at that same formula is actually very useful. It's called the product rule for probabilities. And the reason this formula is so useful is because it allows us to compute the probability of the intersection of two events. If I want to know what the probability of the intersection of two events is, this formula comes in very handy. Let's look at an example. A container contains 35 green marbles, 20 blue marbles, and 4 red marbles. That may look familiar since we did one that starts off like this earlier. 2 marbles are randomly selected without replacement. What is the probability that the first one is blue and the second one is red? Not the same problem we worked earlier. The first thing that you have to notice and to understand is that this is not a conditional probability problem. It starts off and looks so similar to the problem we worked earlier. But this doesn't ask for a probability of something given some condition, this simply asks for the probability the first one is blue and that the second one is red. Not the probability the first one is blue given that the second one is red. So we're not given a condition. We're not saying we already know the second one's red, or for that matter, we're not saying the probability we know the probability the first one is blue. We don't know any of that. We will know the probability before you do either one of them both happening. It's not conditional probability. And again, what it is you're looking for the probability of an intersection, of an and. So this relates directly then to the product rule for probabilities, because that's what the product rule for probabilities tells you how to calculate. That's important. If you work this as a conditional probability problem, you're automatically going to be wrong. You've got to see that this is not conditional probability and how it differs from the ones that are. This problem requires a lot more care. You've got to really think this through. I know now that this is the probability of an intersection, and I know what the formula is. So let me write that out, and then I'm going to. In fact, let's do this first. I want to go ahead and sort of categorize everything, calculate all my important information. I know from earlier that I've got 25 green, 20 blue, and 4 red. So I have 59 total marbles. So let's actually just make a little chart. Before anything is drawn, what happened? What does this thing look like before anything is drawn? Well, let's break it down. They're talking about red, green, blues, and reds. Let's break it down completely by color. You've got green, you've got blue, and you've got red, and then you have your total. So let's look at it that way. In the beginning, you have 35 green, 20 blue, 4 red, a total of 59. Okay. Now, what does the product rule for probability say? It says the probability of the first one being blue and the second one red is, and again I'm using the formula up here, is the probability that the first one's blue times the probability that the second one is red given that the first one is blue. So notice I said this was not a conditional probability problem. However, one step in the solution of this problem does involve a conditional probability. It's just that we're not calculating. The answer to the question is not a conditional probability, but one of the steps in getting the answer involves a conditional probability. So you got to be careful here. So let's take this thing one at a time. The first thing we want to do is find out the probability of getting a blue on the first draw. That should be pretty easy. In the beginning, we have 20 blues over 59 total. Now 20 is 2 times 2 times 5. 59's odd, so it doesn't divide by any of the 2's, and it doesn't end in a 5 or 0, so it doesn't divide by 5. So that 20 59's will not reduce. Now we're going to multiply by. Now here's where we've got to do a conditional probability. This calculation is a conditional probability. So for that part, we have to look again at where we stand, because for the conditional probability part, we know that the first one was drawn blue. So If the blue one was drawn, after drawing a blue, this chart gets modified. So you would still have, and I'm sort of just looking down here, you'd still have 35 greens, but you drew a blue. That's this condition here. So you would have only 19 blues now. Your number of reds would still be 4. But now you would only have 58 marbles left. So looking at that, the probability that the second one is red, looking down here, would be the number of reds, which is 4, over the number of marbles you have left, which is 58. Now that 458 will reduce to 229, so you can save yourself a little bit of trouble here. But actually, they want the probability written as a decimal to 2 decimal places anyway, so you really don't have to worry about that. So you can just write that as 20 times 4, which is 80, over 59 times 58, 3,422, and then divide and leave it written as a decimal to 2 decimal places. So you would have 80 divided by 3422, and to 2 decimal places that would be 0.02. So the probability that the first one is blue and the second one is red is extremely small. So it's really 2%. There's only a 2% chance of that happening. Also, before I move on, I'd like to say one more thing. I'm about to show you an alternate way of doing this involving tree diagrams, and I think it's very useful. So although this is the formal way of doing it using the product rule for probabilities, what I'm about to show you will apply to this problem. So after you learn this new visual way using tree diagrams, you might want to go back and do the same problem that way and see if you think it's easier or makes more sense. But anyway, we're going forward now. I'm going to show you a more visual way involving tree diagrams to deal with these product rule for probability problems. Now, as I promised, I want to use this example to introduce another way of dealing with these product rule for probability problems, and that is using tree diagrams. We're going to use this example to get us through this. It says, Brianna's in a lottery for a dorm room in one of 2 new campus dorms. She will randomly draw a card to get a space in either Xavier or Young. Those are the 2 dorms. She will also draw a card to determine if she gets a room or an apartment once she knows which dorm she's in. The number of cards in each case is proportional to the number of availabilities, and 30% of the available spaces are in Xavier. 80% of the available spaces in Xavier are suites, and 40% of the spaces in Young are suites. So you've got to digest all this information. Now take a moment to look at how I've gathered this information up. It says 30% of the available spaces are in Xavier. That means the other 70% are in Young. They didn't say that, but that has to be the case. They said that 80% of the available spaces in Xavier are suites. So if 80% of the spaces in Xavier are suites, that means the other 20% of spaces in Xavier must be rooms. And then lastly, they said 40% of the spaces in Young are suites. So that implies that 60% of the spaces in Young are rooms. So they gave us 3 pieces of information, and we ended up with 6 because of how the probabilities work. If it's 30% of one thing, it's 70% that it's not. If it's 80% of one thing, it's 20% not, and 40 and 60, so on. You also notice that I have a tree diagram set up over here, and I think you can guess how it works. The first choice the student has to make, it gets the first choice that is made for the student by the lottery is whether they're in Xavier, which is X, or Young, which is Y. And once they choose, get chosen for Xavier or Young, they either get put into a room or an apartment. So that's the R and the A. So I need to transfer these probabilities into the tree diagram. So if 30% of the rooms are in Xavier, that means the probability of getting Xavier is 0.30, 30%, or just 0.3 if you'd rather. And the probability of getting Young is 70%, 0.7 or 0.70. Now once you know you're in Xavier, 80% of those are suites. Actually, I wrote A for apartments, but I don't want to change that. Let's just say apartments are suites. I don't want to redo this just because of the wording. Anyway, for our purposes, apartments or suites, same thing. So if 80% in Xavier are the suites, or as I've actually started off writing, I call them apartments, but just make that translation. That means that 20% are rooms. If you get Young, 40% of the spaces are suites, or A for apartment as I've written it, which means the other 60% are just rooms. So just to stay on with my notation, I used A for suites, which we'll say means apartments actually, and I used R for rooms. Okay, you'll notice I've sort of corrected my little typo. I was using suites and apartments interchangeably, and I didn't catch that until I started the problem, and I definitely don't want to do this again. So I just modified it. I was using suites and apartments to mean the same thing, and I just now caught it. So we're going to call them apartments from now on. In any case, there's your tree diagram. There's a 30% chance that the student will get into Xavier, a 70% chance they'll get into Young. Once they get into Xavier, there's an 80% chance of getting a room, a 20% chance of getting an apartment. Once they get into Young, there's a 40% chance of getting a room and a 60% chance of getting an apartment. So I took all that information and summarized it and created probabilities in a tree diagram. And here's the question I want to ask, at least here's the first question I want to ask. What is the probability that Brianna gets an apartment in Young? In other words, what's the probability they get in Young and get an apartment? So this is a probability of an intersection. And if you read it, it doesn't even use the word and, but the only way you can interpret it involves an intersection. What is the probability that Brianna gets an apartment in Young? That means Brianna gets an apartment and it's in Young. So this is a probability of the intersection of those two events. So by the product rule for probabilities, we know that the probability of getting into Young and getting an apartment is the probability of getting into Young, I'm just going to use Y for Young, times the probability of getting an apartment, I'll use A for apartment, given that the student got into Young. So if this is Y and this is A. Well, what is the probability of Y? What's the probability of getting into Young? Well, the probability of getting into Young is 0.70. I can read it right off the tree diagram. Times. Now, what's the probability of A given Y? In other words, what's the probability of getting an apartment given that the student got into Young? Now, this is where the tree diagram just shines. If you already know that getting into Young has already happened, that means you've already traveled down this branch. So you're already standing right here. You're at Young. So then, what is the probability you get an apartment? Well, that's easy too once you see where you are. The probability that you get an apartment once you know that you're in Young is 0.60. So it's the product of these two numbers. Notice that the probability of getting an apartment given in Young is already on the branch. You're not calculating it, you're really just picking the number off the branch. And so if we take our calculator, 0.7 times 0.6 equals 0.42. 0.42. So there's a 42% chance that Brianna gets an apartment in Young. But the main thing I want to say about this is when you're doing intersections and you have a tree diagram, the AND is just the product along the branch. That's the appropriate branch. So once I get my tree diagram set up, I know an AND is always going to multiply down the appropriate branch. Well, the appropriate branch is the one that has Young and an apartment. So that's this branch right here. Just multiply down it. So even though the product rule for probabilities will certainly give you the answer, if you've got a tree diagram and you're looking for this intersection, just multiply the probabilities down the appropriate branch and you have the answer. So that's what I'm trying to get you to visualize the product rule for probabilities as being multiplication down the branch of a tree diagram. And I do want to give you just various questions that could be asked about this situation. So let's ask something really simple. What is the probability that Brianna gets housed in Xavier? Well, that's so simple once you get the tree diagram set up that you simply have to look on the tree diagram and realize the probability that Brianna gets housed in Xavier is 0.30. So the point I'm trying to get across is once you get these problems set up, you can be asked a lot of questions. Some questions involve multiplication. Some questions are simply going to involve reading a number off of one of the branches of the tree. So you have to think, you have to put your thinking cap on, you have to concentrate and make sure you're answering the question that's being asked. Well, we've got this problem up. Let's ask even yet another question about it. This time, the question is, what is the probability that if Brianna gets housed in Xavier, she gets a room? So, again, you have to read carefully and you have to be very careful. It says, what's the probability that if Brianna gets housed in Xavier, she gets a room? So they've given you a condition. Brianna gets housed in Xavier. That's the condition. They've already given you a condition. So this is actually a conditional probability problem. This is the probability that she gets a room given that she's housed in Xavier. So the condition, remember, always goes in this position. The probability she gets a room given that she's in Xavier. Now you could go through the definition of conditional probabilities and say, well, that's going to be the probability that she gets a room and gets in Xavier divided by the probability that she gets in Xavier. You could, but my point here is you don't have to do it that way. If you can interpret this tree diagram correctly, you don't have to do this. You can avoid using this formula. And here's how. It says the condition is she gets housed in Xavier. So if she's housed in Xavier, then she's already traveled to here. And now you're saying that's already happened. Well, if that's already happened, this stuff back here is in the past. It doesn't matter anymore. That has already occurred. So really, at this point, you're saying, what is the probability once you get to this point? What's the probability of then getting a room? Well, you can look and see now that's 80%. So the probability that Brianna gets a room, given that she's in Xavier, is 0.80, and you can read it right off the chart. So here's the bottom line. Your normal, I'll use that word, although I'm not going to define it. Your normal probabilities are on the initial branch. Your normal probabilities lie on the initial branch. The first branch are your normal probabilities. That's like the probability, in other words, the probability that Brianna gets in Xavier, the probability that Brianna gets in Young. Just straightforward, plain, normal probabilities. The branches that follow the initial branch are always conditional probabilities. So if you can remember that, your conditional probabilities always lie on the branches after the initial branching. So if you can remember it that way, the very first branch is just a normal probability. Anything beyond that is a conditional probability conditioned on what came before it. So begin thinking about that, and let's do another one. Now I want to sort of build your intuition a little bit by asking some other questions. And there are just numerous things I could ask. But I might ask, for instance, what's the probability that Brianna gets in Xavier and gets an apartment? Okay. Intersections are always products down the appropriate branch. So I'm going down the X branch and the A branch. So without much thought, once I learn the procedure, I know that the answer will be 0.30 times 0.20. Which is 0.6. So there's a 6% chance that Brianna will get in Xavier and an apartment. What's another question I could ask? What is the probability that Brianna gets a room given that she got in Young? Remember, a conditional probability one time. An intersection is a product down the main diagonal. A conditional probability jumps straight to the interior branches. But where? Well, let's look. We want the probability that Y has happened. They got in young. Brianna got in young, but the probability of getting a room. Well, if you go down the young branch and the room branch, you can see that you're looking right here. It takes some getting used to, but when you have a conditional probability, it will always be one of the numbers sitting on one of the interior branches. You have to figure out which one. It's the one that has the R. It's down the Y branch, and you're looking at the R branch probability. So conditional probability is never a product when you look at it from a tree diagram perspective. It's simply one of the interior branch probabilities, whereas an intersection is always going to be a product down the appropriate branch. And of course, if I just wanted to know what's the probability that Brianna gets into young, then it's just one of the initial branches, and it's just the number right there. It's just the probability. So the normal probabilities that don't have a condition, don't have an and or an intersection, those will always be one of the numbers on the initial branch. A conditional probability will always be a number on an interior branch, and a product, an intersection, an and, will always be the product down the appropriate branch. So intersection, product, conditional probability, an interior, just a number right off the interior, one of the interior branches, and a normal probability that doesn't have an and or a condition is just one of the numbers on the one of the numbers off the first branching. And if you can get that into your head and practice it, you're well ahead of the game. You don't have to stress so much, and it becomes more interpreting the problem, and then the answer flows easily rather than having to work hard to get the answer once you've interpreted the problem. So you still have to interpret these numbers right, get them on the branches right, but once you've got them there, you can answer a whole series of questions about them without having to work very hard beyond that point. The hard work goes into getting the branch probabilities right. Now I'm going to talk about the concept of dependent and independent events. First, going to give you the formal definition. Events F and G are independent if the probability of G given F is the same as the probability of G. And if the probability of G given F is not equal to the probability of G, then F and G are said to be dependent. And what I'm going to say about that is, although this is the formal definition, for our purposes, what we're going to do with this, just an intuitive idea of dependence and independence is probably going to be good enough. So here's the intuitive idea. Intuitively, we say that two events are independent if one of the events does not affect the probability of the occurrence of one of the events does not affect the probability of the occurrence of the other event. For example, if I flip a penny and a nickel, if I let A be the event that I get ahead when I flip a penny, and I let B be the event that I get a tail when I toss a nickel, flip or toss, whichever you prefer. I think you can see just intuitively that those two events are independent. What I get when I toss or flip that penny, whether it's head or tail, is not going to have any effect at all on what I get when I turn around next and toss the nickel and get either a head or a tail. So those events are obviously independent. They just don't have anything to do with each other. And that's the intuitive definition of independence. Now let's look at another example. This time let A be the event that you draw a spade from a regular deck of cards. Without replacement, that's important. And let B be the event that you draw a second spade. Now, are these events independent? Well, you may have already thought this through enough to figure it out, but in the beginning, you have 13 spades, 52 total cards. If the event A is drawing a spade, so if you let event A happen, A happens, if you let A happen, meaning you get a spade, then you're down to 12 spades and 51 cards total because you're drawing without replacement. That means you're not putting the card back in. So the question is, does drawing that spade out affect the probability of drawing a second spade? Well, obviously it does. If you draw one spade out and now you only have 12 spades, the probability of drawing a second spade is going to change. The probability of drawing the first spade is 13 out of 52. But the probability of drawing the second spade, if you don't put the spade back in, is going to be 12 out of 51. So it's had an effect. So events A and B are not independent. A happening affects B. So these events are dependent. If one has an effect on the probability of occurrence of the other, they're said to be dependent. Flipping two separate coins don't have anything to do with each other. Those are independent. I think just an intuitive definition of dependence and independence is going to get you through here. Okay, one more thing and we'll leave the dependent-independent alone for a while. Very similar example. You're still drawing a spade from regular deck of cards, but this time you're doing it with replacement. You've got to be careful because sometimes they sneak things in and you don't notice it. If you draw a spade from a regular deck of cards, there are 13 spades and 52 total cards. So the probability of the event A, which is drawing a spade, is 13 out of 52. Of course that reduces, but for my purposes I don't care. But what I do want to say is that I'm putting it back before I draw again. I'm doing it with replacement. So the second time I draw, I'll still have 13 spades and 52 total. This is the first draw. This is the second draw. But it's with replacement. So the numbers don't decrease. I'm putting it back in. So the probability of B, which is also getting a spade, doesn't change. It's 13 out of 52. The two events do not affect each other. The probability having one happen does not affect the probability of the other one. It stays the same as 13/52. Therefore, these two events are independent. So you do have to think about this before you just jump to a conclusion. But if one event has no effect on the probability of the current occurrence of the other event, then the two events are independent. Stop.